And we have the summarization note taker as well. Okay. Hey, everybody. Welcome to Planet Cassandra Global Meetup. This is our second official meetup of the year. Last month, we talked about Kafka change data capture with Mr. Bergen. And this week, we're going to be talking about just Cassandra data modeling, optimization. I'd like to just introduce you to everybody that's on the organizer team. My name is Rahul Singh. We have Sohail from, you want to give a quick intro real quick?
Hi, my name is Sohail. I'm happy to be here, and I'm one of the co-organizers of the Planet Cassandra, and I hope you have a great session today.
Excellent. Aaron, you want to give a quick intro?
Oh, sure. Hey, I'm Aaron Pletz. I work for DataStax, but I've been a part of the Cassandra community for about 12 years now, 12, 13 years, something like that. I've even written a couple of books about it. So, yeah. But hey, happy to be here, happy to help out, and happy to answer any questions. So, hey, thank you, everyone.
Excellent. Bernardo?
Hey everyone, this is Bernardo, originally from Spain, but based in Seattle right now. And yeah, I've been contributing to Cassandra for like 3 years now, something like that. And eager to know more about this data modeling talk today.
Excellent. And yeah, sorry, I didn't say anything about myself. My name's Rahul Singh. I contribute to Cassandra in a different way. I like organizing the knowledge. So I've created Cassandra.link and have been helping recreate planetcassandra.org. And I'm looking for folks to help maintain and build planetcassandra.org together. So without further ado, I want to get started with the talk. Hartmut is a software architect. He has a lot of experience in distributed systems, Cassandra, Kafka. So I'm really interested on his perspective, because that's my game as well, distributed platforms. And he's got a lot of content to cover. But take it away, Hartmut. Go ahead, and it's your show now.
Yeah, thank you. So let's share the screen. And yeah, you should now see the cover page. So
yes,
let's get started. Yeah, today's talk, I think it was named, the title slightly different in the meetup page, but it's maximizing Cassandra's potential. So I want to cover like the entire everything that's interesting as an architect and also as a developer, building like applications with Apache Cassandra as a database or data store. So I want to cover and give tips on schema, on how to do queries, also on parallel access, since you usually need to denormalize data with Apache Cassandra, and why I think reactive programming is just a wonderful, perfect fit when you work with Apache Cassandra, and yeah, how that can also help build efficient and robust and scalable applications on top of Apache Cassandra. So yeah, my name is Hartmut Armbruster. I'm currently based in Berlin. I'm, like it was mentioned, software architect, software engineer, doing hands-on development. I'm an independent consultant, have been for more than 16 years. Worked for different companies, different industries, in finance, in government, in security, in transportation. And yeah, I'm interested in all things scalable architecture, backend, front-end data, and stream processing, just to mention a few. And yeah, today I just want to bring my perspective, share some ideas, get things you hopefully can take away with when you approach your next project. And yeah, having said that, let's just get started. So before we actually start with the actual content, just to cover again Apache Cassandra for everyone that's new or interested in Apache Cassandra and not already experienced with deep knowledge. Just to mention, it's been created at Facebook in 2008. It's been inspired by Amazon DynamoDB or Google Bigtable, and it became a Apache top-level project in 2010. And yeah, I think the most fundamental thing is that it's highly scalable. So it scales linearly. You can add nodes to just add compute and storage. You can run clusters with like 300 nodes and terabytes or petabytes of data. I think there are better people to tell you about the scale that's out there in production. But yeah, there are like industry giants like Netflix, Apple, Spotify, Uber, just to mention a few. They all leverage Apache Cassandra in one way or the other for all of different use cases like real-time analytics, personalization engines, fraud detection, IoT. And yeah, with the recent 5.0 release or the upcoming 5.1 release with vector search, I think there were other talks introducing all of that, but yeah, Apache Cassandra is far from being outdated and yeah, kind of ready for the next steps with as a backend vector search for AI and so on. So yeah, it's a distributed NoSQL database and known for fault tolerance, high availability, and has also data centers from day one really embedded into its architecture. So you can have multiple data centers in different regions across the globe and keep data replicated and in sync. And yeah, all of that is why Apache Cassandra is super exciting and is great and can drive like big data and many use cases. But it's also challenging to work with Apache Cassandra due to that distributed nature and due to some architectural change decisions or that are done, just the nature how Apache Cassandra works. And yeah, that's what I want to talk is about, to just share some ideas, some examples, how you can still kind of use it, work with it, and make the best out of overcoming limitations, pushing the boundaries, how you can still build applications on top of Apache Cassandra in a very efficient way. So yeah, moving on to the agenda. On the right-hand side, this is my example I want to work with today and what this is about. The talk is structured around its social platform feed. And yeah, what we want to do is we want to design the data layer at the backend to implement a RESTful API to drive kind of whatever application, mobile, web, to build this wireframe of social platform feed. And we're aiming for a pretty snappy response time of less than 10 milliseconds, and that at scale, like you would expect from a social platform, from like a global platform. We'll learn more in a few minutes. So yeah, agenda, just to cover quickly, use case I just mentioned. We're going to start with the access patterns, covering the queries and work out the schema, and then also the process flow, how we need to put all of that together to build our REST API. We'll do some iterative refinement to improve our architecture and our designs and the schema. And then we'll move on to why non-blocking and reactive programming works perfectly well with what we want to build. Also have a code example and some results in terms of kind of benchmarks or traces, and wrap up with some conclusions. So as it was mentioned earlier, or who might have joined a bit late, I will take questions at the end. So, but yeah, feel free to pop them in the chat, and we can all address them after my talk is finished. So, starting with just the functional requirements to talk about a bit more in detail about the use case. Like I mentioned, building a RESTful API for a social platform feed. Feeds will have posts, so you can matching something like a Reddit, where a subreddit in this case would be thriving dev architecture, and all kind of the group members or the feed members can post great posts, and they are all listed within this feed. And yeah, posts can be listed, they can be liked, bookmarked, and commented on, like all the usual. No surprise here. I will have like an endless scroll, which means you obviously can scroll down and fetch more posts and paginate. We also want to do something I call search after pagination, which means you might know this from Twitter, former X. When you open the feed and you scroll down, since it's kind of a live social media platform, there can be new posts created at any point in time, but you don't want to mess up your pagination. That means you need to kind of pin the point in time when the user has opened the feed. And then as you scroll down, you don't mess up the pagination, but you always kind of make it based on that point in time. And at the top, you can show like updated every now and then. There are now 13 new posts, and you click the button and they will load, and you restart the pagination from scratch. Yeah, that's kind of the functional parts of this page to fulfill everything that you need to display and build that actual product. So yeah, just to give a quick example, or essentially the core of this talk is that we want to build all of that in like a single endpoint, actually, where you fetch a page of posts. So all the data required, we want to deliver all of that with that single response to a request for that API. And that is also valid for a guest user, or it could be an authenticated user, meaning it's specific data to each individual user, which might have liked or bookmarked certain posts. We'll get more details in a minute. This is how it might look like. So it's a kind of complex data structure. It's not flat data. You have arrays, you have nested objects. But before we all get lost in that JSON, let's just kind of break down all the data elements and go one by one. Starting simple with the feed, no surprise here. It simply has a name like Thriving Dev Architecture. It obviously has an ID, and you can order. I think this is not too relevant to our queries and the schema, but this is kind of the overall starting point in our wireframe. Then we have posts. Post has, of course, a post ID. It belongs to a feed ID. It has a user ID, which is the author. It has some text, our actual content, a timestamp, and then we also have the number of impressions, number of likes, and number of comments. And the next part is what I call this session user specific information. So the authenticated user that opens the feed page will obviously get kind of indicated that he has bookmarked a certain post, or he has already liked a post. When he can click it, he can kind of unlike or like new posts, but it should be visible. So it's very specific information to the user calling our API or opening the application. And yeah, it's essentially just a relation of user ID to post ID and a timestamp when he actually has clicked that like button. That's this part of the data. And last but not least, we have user information. So the author of a post, just the usual username, name, avatar, nothing special. All of that together, just for reference, it's recorded, so you can go there and take a look. So moving on to access patterns. So now we actually want to create a schema. We want to build this. And what we start with is the access patterns and our queries to read all of that data from different tables from our Apache Cassandra database and schema. And what you do with Apache Cassandra is you always start, or it's recommended to start or work in kind of a query first approach. And that means you design your data model based on how it will be queried by the application or by all different applications or consumers that need access to your data. And the reason is essentially that in Apache Cassandra, you have, like compared to a relational database, limited query flexibility. So Apache Cassandra has no foreign keys. You cannot do joins to other tables, and you cannot do subqueries. So yeah, that's one reason. There's also kind of limitations on indexing. There's secondary indexes, global indexes, but ideally you should use them more sparingly or just avoid them if you can. And that means you just store your data optimized for how you actually want to read it. And yeah, the steps to do this query first approach is just to start with those access patterns, which we're going to do now in the next slides. Then we define our queries, which leads us to the primary keys, which leads us in the end then to the final table and the schema of our for our application. So yeah, let's get started with that. The first access pattern we need for that page, pretty obvious, would be to get the list of posts to render. And it needs to be paginated, as mentioned before. It will have an order. In this use case, we have it from the latest descending. And yeah, we want that query pinning. That's the first access pattern. The second is we need to get this stats, meaning we want to get the number of impressions and likes and comments, and we want to have that in kind of real-time updated when your neighbor clicks a like button and you refresh, you should see that in the API response. The third access pattern is to get this session user relationships, which means do I like this post, or has the user bookmarked this post? So you can highlight that in the front end. The fourth pattern is just to get the author of a post by user ID. And last but not least, we also want to show this kind of how many new posts have been added since I started looking at this feed. This is kind of this show 13 new posts at the top. So yeah, and with that, we will get started with our first access pattern to get this list of posts. While we start with the queries, just for the talk, there's the first table called post. We have like for before in the entity declaration, we have a feed ID, post ID, and so on. You can read that yourself. And our first query to fetch the topmost page of posts for a particular feed looks just like that. So select from post where feed ID is so and so with a limit of 20. This will give us the first page of 20 posts. And kind of the second part of that, obviously, if we need to fetch the follow-up post page, is that we add another criteria that we say we don't do like with an offset. We are just going to work with the post ID. So we say, yeah, same query, same conditions, just we add that the post ID now needs to be smaller than essentially the last ID of the last post of our first or the previous page. And we also fetch 20 of that. And to make this work, there's also those details that we now need to define our primary key accordingly. And if you look at the post table, it is a bit of kind of advanced. You should know somewhat how the table schema definition works in Apache Cassandra. But looking at the primary key, it has two portions. The first one is the feed ID, which is called the partition key. So all posts for one feed are stored in a single partition. And then we have a second part, which is the post ID, which is our clustering key. And this is how essentially the order of how our posts within a single partition are actually stored on the disk. And we say the clustering order is also by post ID descending. So when we query, using those queries on the right-hand side, query our data by feed, we will automatically get the data ordered by creation date descending. And you might be asking, how is this working? What are those strange IDs we see here? Just to cover that quickly, I chose something that's called ULID. It's kind of sort of a UUID. This is which is canonically encoded with 26 characters, so it's URL safe. It's a perfect fit for anything kind of REST API or the web space. And it essentially consists of a timestamp portion and then some randomness. And it's called universally unique lexicographically sortable identifier. And the benefit is really that you can generate them randomly, many different unique IDs per millisecond, and you can also sort them. And you can also extract kind of the timestamp from our ID. There's also like a UUID version 7. This is quite similar. It's a bit different approach, but it works the same way. It's just not encoded into kind of alphabetic characters. You could give a separate talk on this if you're interested. There are the links at the bottom. I highly recommend to look at this when you work with kind of time series data, like in our case, posts of a social media platform. So moving on to, essentially we have fulfilled our first access pattern, moving on to the second, which is now we want to get the stats for a post. So the number of impressions, likes, comments. And to do that, we just create another table called post stats. And here we have impressions, bookmarks, and so on being counter type columns. And when we want to get the stats for one particular post, we can just query it by post ID. We have a primary key post ID, and we have our data. Here you might be asking, why not put those columns directly in the post table? Why do we need, or why do we choose to do two different tables? The answer is this is one of those limitations in Apache Cassandra, which is when you work with counter type columns, you cannot mix them with other columns apart from the primary key. So for this reason, you cannot just put a counter of impressions into the post table. It's just not allowed to just optimize how Apache Cassandra works and can do like this atomic operations on counter type columns. So this is why we have a separate table. Again, if you're interested, you can read all of that in the documentation or just approach me or any of the other members of all the organizers later. So second pattern is fulfilled. We have a second table. Let's move on to pattern number 3 to get this session user relations of a user to a post. It's actually pretty straightforward. It's just a table we call user likes post. It has both IDs, a timestamp. The primary key is the user ID and the post ID. And when we want to query that, if a user likes a particular post, we just do it straightforward, select by both IDs. And we create another table, user bookmarked post. And yeah, same query, just the second table. So third access pattern also fulfilled. Moving on to, the author information. So just a user table with all the fields, and we can just query a user by ID. So nothing fancy here. Fourth pattern also fulfilled. And the last one is to get this new post count. For that, we don't need a new table. So we have our post table as a reference on the left side. And what we can do is we just do a select count from post. And the query condition is essentially just kind of the reverse of what we use for the pagination, where we have this pinned point in time ID we can essentially just generate such a ULID when we open the feed page or when we first query the REST API. And then we just use this ID to say now just query all the posts that are newer than this post ID. And this works. This is a working query, but here's kind of the first small kind of hint or tip I want to give before we start refining and optimizing the schema and all of that refinement process. You should be careful working with select count. Reason is, if you do a select count, it typically forces the database, that being Apache Cassandra or any other database, to do a full table scan to get that exact count based on your conditions. So it can be an entire full table scan or basically covering an index, or in this particular case, it would cover the feed ID partition and with an extra filter. It might be fine for this use case, but it can go quite wrong and put a lot of pressure and on I/O and network when you query using select count. So just like one first small optimization, which is actually more on the functional requirement, would be that you can also do, like as a trick in this use case, you don't actually need to tell the user always the exact count of new posts. If it would be 13,189 new posts since you opened your feed, that exact number actually doesn't matter. So you could just decide from a product perspective, we want to have an exact count up to 100, and everything beyond, even for the user in the wireframe, we just say, well, it's kind of one new count, 72 new posts, or just more than 100 new posts. And that would be good enough for the user. And it would also, in terms of that query, where we just now not use a select count, but we just use a select post ID with limitations, would put less pressure on the database. I actually got used to get the most questions about this particular query. Find me later. I need to move on to cover the rest of my talk. So yeah, it should get more interesting now. So we have all the access patterns solved. We have a first schema with the tables holding our data with primary keys, and with some first queries to get to store and also read all the data we need. So let's move on to how we would now actually build that process flow in our backend code to put all of that together, to do all of those queries of our different tables, to create like a full page of 20 posts with all the information, session user related, the impressions and everything. How do we need to put all of that together? So, and this is kind of the first most basic approach, where we just say we do everything sequentially. We just start with our first query. I hope it's readable. Well, we are online, so of course it's readable. We get our page of posts, and then for each post, we just iterate over this page. And for each of those 20 posts, we just get the stats. Then we also query and get if the user likes this post, then we query if he bookmarked this post. We also query the author, and we do that for each post, meaning if we do the math, we are actually doing 81 queries to our database, and we're doing all of that one after the other. So subsequent steps of I/O from our backend application to the Cassandra database. And yeah, oh my God, that's a lot of queries. And can we do that in less than 10 milliseconds? I'm quite sure we cannot. So yeah, I think surely we can do better. Which means now we're kind of going to start to do something I call the iterative process of schema refinement. And it has different elements where we, just starting from the left, we basically start with an initial design, which is what we just did. We kind of put everything together, start working on the queries, create the schema, and to fulfill our functional requirements. And now we can start working on the access patterns. We can work on the schema itself. We can work on the process flow. And we just kind of keep repeating all of those elements where we can try to optimize until we either can no longer optimize what we want to do, or where we have a sufficient optimized solution. Depending on how critical your use case is, you can spend more time on that, or yeah, you don't need to do that for each and every single small requirement. But here we are talking about kind of the front page, kind of one of the main pages of a social media platform. So it's very critical to make this performant and also resource efficient, not too much pressure on your database, also not on the backend. It needs to scale, it needs to perform well, it needs to be robust. And also you don't want the user to kind of wait 3 seconds for his response. So it should be snappy, it should provide a good experience. So again, this is now just this example to take this use case and show what you can actually do to improve. So the first step is we go back to our database schema, and we start with those relationships. It's a very simple example. So we've had 2 tables, a user likes post, and we have the user bookmark post, and they were actually, if you noticed, almost identical, just had a different name. So why should we use 2 tables? Let's just put them together into one table. We add a new column relationship type. We add that to the primary key, also to the clustering order. And now if you want to know if a user likes a post, we can just query user ID relationship type like and the post ID, and we get our information. And we can do the same for bookmarks. And now, why should we do 2 queries? Can we not just fetch all information in one go for a user to a post? So question is, yeah, why not just select from our table with user ID, post ID? The answer is, again, this is kind of one of those complexities working with Apache Cassandra. You cannot do this. Reason is you need to use all primary key columns, or at least you need to keep the order of the primary key columns. So you could do a select by user ID and relationship type and no filter on the post ID. That's valid, but you cannot skip the relationship type in the middle. You need to keep the order, or have all 3 of them in your query, or you can do allow filtering, which puts more pressure on the database. So you should try to avoid. But actually, in our use case, it's kind of a simple trick, meaning we only have 2 relationship types, and they are static, and we know of that. So we can easily say, give me all the entries of this table for a user ID, but the relationship type is using an in query, and we just list all of them, which is just 2, where it's either a like or a bookmark for this post. So why are we doing all of this? Essentially just going back to our process flow. We now have 1 less query in our loop, which means we're down from 81 to 61 queries. We're still doing that sequentially. And yeah, we improved, but I think we can still do better. So leading us to the next optimization we are going to do is on the process flow, so not on the schema, which means actually kind of those queries 2, 3, and 4, they have no dependency between each other. So there's no reason to do first query 2, wait for the database to respond, and then we do query 3, and then do query 4. So we can just parallelize them. So we can just submit all 3 queries to the database, and when all 3 of them have returned, we can do that for the next post. So using parallel processing, we still do the same number of queries, 61 queries to the database, but we only have 21 subsequent steps. We have the one on the top, we query the first page. And then for all the 20 posts, we do 3 queries in parallel. And in the end, we combine all the information and respond. But we can still do better. Well, let's see if we can. So going back to the data schema, looking at the post stats table, we're just again going to modify the post stats table. So the first version of our table had the primary key post ID, which allowed us to do a lookup by ID. But now what we're going to do is we're just going to add the feed ID. So we essentially will have the same primary key as the main post table. And what that allows us to do is kind of use the same trick that we did for the bookmarks and likes, that we now just say, well, instead of doing lookups for each individual post, we can select all stats for the feed ID, which is our partition. And we, of course, know while we're displaying posts for one particular feed, and we just do another inquiry where we just list all of our 20 post IDs that we are going to work with. And that means instead of doing looping and doing 20 queries to look up the stats, we are down to a single query for one page of posts. And actually, if we go and take a look at our user post relationship table, we can actually do the same trick here as well, which means we can select all the relationships of the current user to a post for this user ID for both relationships types, so likes or bookmarks, and for one of those 20 post IDs. Meaning we get all the relationships of this user for our page of 20 posts. And with this optimization step of tuning basically just a query, really, how we're going to query in a clever way, and go back to our process flow, we can get rid of the entire looping process where we say we just iterate over all 20 posts, which means we do our first query to fetch our page, and then we do that kind of bulk query to get all the stats for all 20 posts. Then we get all the relationships, both likes and bookmarks for all 20 posts. And what's left is that we only need to get all the authors of our 20 posts. And we just in the backend, we can actually just say, well, there's a good chance it's not 20 different authors, but maybe there are some authors that have written multiple posts. So we just, of course, do not fetch the same user 5 times. We just fetch it once. So we just do a distinct list of user IDs, and then we query all those users in parallel. And we do, again, this step query 2, 3, and 4, all of that also in parallel. And we combine everything and we respond. And yeah, doing the math, we started off from 81 queries and 81 IO steps to the database. And what we're left with, the process flow right now, is we do from 4 queries, if we would just have a single author of all 20, up to 23 queries if we really have 20 posts from 20 different authors. And we do all of that in just 2 subsequent steps due to our parallel access. And I think that's at least from my point of view a quite good result. It will be less pressure on the database, and we can do that in a very efficient way, also very performant for our low latency API. And actually, another idea where you could improve that is this user information is something that does not change often, so it's very slow moving data. And it's also a good candidate, which you can just also use an in-memory cache. So if you scroll down your feed, there's also a good chance on the same feed there's other posts from users that authors that you might have fetched earlier. So you can just read that from cache, and you would have even less queries to your database. And yeah, I think that's that success that I see pretty much worthwhile spending this yeah effort on our optimization of queries, of schema, and of all of that to refine our solution, our end-to-end architecture to make create the best solution. So, but we're still not done. Let's move on to that's kind of all the theory, all the design, but we also need to implement our backend. So I will move a bit quickly. I think we're running out of time. So our application stack, I choose a non-blocking I/O, so Apache Cassandra, client and drivers were non-blocking and asynchronous from the very beginning, I think from the first release drivers. And I'm also choosing reactive programming as kind of the programming paradigm to work with, and Kotlin as my programming language. Yeah, reactive programming, actually, I think due to time limitations, I will need to skip this. If you're interested, again, just contact me, reach out after, or there's also the DataStax or Apache Cassandra community Slack, or I think it's actually the Apache Slack. Maybe someone of the organizers can provide a better solution where you can come and discuss all things Apache Cassandra. But yeah, my choice for this example, it's also to leak that right now. It's fully implemented, available on a GitHub repository. So you can also go there, take a look, and just spin it up yourself on the Docker Compose stack and play with it. It's implemented with Project Reactor, RX Java, or it's actually not. This is just a popular active programming frameworks. Getting confused here. My choice is to use Quarkus and Mutiny, and Apache Cassandra and Kotlin. So let me take a breath. I think I'm a bit hectic. So just recap, this is our process that we want to implement. And now comes this code example, how that looks like implemented with reactive programming, with Mutiny and Quarkus. And it's a bit more complex than that example I'm showing here, but the benefit with reactive programming is that it just fits perfectly well to this process we have defined. So we start off with the request handler. We get the parameters like the kind of the page pagination size and that post ID we want to fetch based on. And then we just do our first query, which is get that page of posts. So this is kind of underlying, obviously just using sending a query to the database in non-blocking and asynchronous. And then we do our second step, which is our highly parallelized pattern of doing everything else in parallel. And in reactive programming, in Mutiny, it just is implemented doing like a transform to uni. So we get our list of posts from that first execution. And then we just do a uni combine all of the following. And we do query 2, query 3, and query 4. Query 4 under the hood is again just another kind of uni combine of that distinct list of authors. And when all of those respond, so if you get all the responses from the database, you just get that back as a tuple. And then we have just a method toPosts response DTO. So this is just a simple transformation where we pass in all the responses from our queries and just map that back to our actual response DTO. We can also do failure handling. We could have retries implemented. We could have a timeout. So this is why reactive programming is kind of super efficient to do all of that. And everything is non-blocking. So you can do, while you're waiting for responses from Apache Cassandra, you can the backend can also process other requests from the API. So this is how it looks like, and it's actually highly complex under the hood what happens, but it's super simple to read and to maintain. And it also maps perfectly well to that process design that we actually figured out or designed. Yeah. And yeah, just last but not least, again, this is again the summary, how the response will look like. And just to recap, this is the information, just a meta block from the API. Then we have some information for the post. We have the author. We have the stats from a different table. We have the session user related information. This is how all of that maps together to a single kind of data element that we package in kind of a bulk list, paginated list of posts in our API. And to really close and show how this actually works. So this is a live trace from my experimental stack running on local host. So it's not necessarily one-to-one into how it looks like in production. But we do know the response times of Apache Cassandra and the latency. So it's not far from the actual thing that you will also be able to run at scale for an actual product. And it also just shows perfectly those two subsequent steps of queries to our database. We have that first select from post, and then we do all of the remaining queries. We do all of them more or less in parallel. And we do all of that entire API request processing in 3.72 milliseconds. And this is kind of all the data for a social platform feed that you can actually scale on kind of a very big way. Yeah. So my conclusions is, yeah, if you put the effort in and create a tailored database schema for your use case, and you also work with parallel access, parallel process flows to further optimize doing many queries in parallel to your database, and you do that with non-blocking I/O and reactive code, you can build very good and robust solutions and applications. But to wrap up, again, it's not all, you cannot really go out there and do all of that. There's a few more details when you would actually want to put that into implementation for that use case. I'm not saying, telling you for your next small project, you should always use Apache Cassandra as your database. So it should be clearly an informed decision to choose Apache Cassandra. For data will be denormalized. It will be indexed on write, so you need to, it's just less flexible how you change or add new columns or migrate data. It's a lot more complex than with relational databases, as an example. So you need to also have the complexity of working with eventual consistency. There's like more information, not more details here, something called keyword hot partitions or bucketing, or the bucketing is the solution. In this example, I just chose the feed ID as the partition key. If you would actually have a very big feed in real life, it could easily get too much data for a single partition. So you need to further bucket that down in, for example, like monthly buckets for a single feed. Migrations can be expensive. Reactive programming also, if you do not have a team, it comes with a learning curve. It's a bit harder, or getting used to do testing, debugging, and troubleshooting. And just as a final note, a lot of this does not only apply to Apache Cassandra. You could also use that with other databases. basically that part of optimizing a process flow and using parallel or reactive programming. And last but not least, a good example, Blue Sky, an actual social platform out there in the wild. They also used a very good pattern. So they did not start with Apache Cassandra from day one, but they started with Postgres to work out their product and kind of build the product, more features over time. And I think after a year, when the requirements were all known and matured, yeah, when they did fully understand the data, they actually moved to Apache Cassandra and kind of moved to a version 2 architecture. And yeah, with that, I think I'm at the end of my talk. And yeah, happy to answer questions. Was hard to keep focus.
Thank you. Yeah, amazing presentation. Hartmut, if you could just stop sharing your screen so everybody can see each other. There we go. So we have about 5 minutes for Q&A. We have one question that was in the chat, which somebody said it kind of maybe relates to your bucketing issue. Why is not time UID type for post ID? From Dimitri.
I think that's my personal preference. I think I showed the UUID version 7. I think that was one of the earlier ones. I'm not sure if it was version 1 or 2, which is also time-based, but that's not recommended. But UUID version 7 would work just the same way.
Right.
Yeah.
Awesome. So I've got a couple questions, but I want to give everybody else a chance to go. Okay, cool. So yeah, I think
let me just also I will share. I can quickly find it, the actual repository where you can also go again and look at. I think it was also shared on the last slide. So since it's recorded, you should be able to find that. Yeah, if you want to take a look and play with, you can find all the schema definitions and the implementation there.
Awesome. Very cool. So yeah, thank you. Appreciate you going through this. And this is maybe more kind of a comment and then question, I find it that when we do Cassandra data modeling, it's really helpful to kind of ask how your REST API would be designed. And so when you think about it, like, what is the GET request going to look like? You don't think about, you think about it from a normalized perspective. And I think that's how you showed it, right? This was the requirement of REST API. This is what we need. And eventually it's like, how do we make everything else kind of fall in line with being optimized from a partition query? Now, there are some modeling methodologies. I think even DataStax had a while ago the Chebotka diagramming methodology, which eventually gets to kind of where you're going. So, what would you say is your experience with like using something like that as a way to systematically design it versus looks like from your experience perspective, that's the way you've designed it?
Actually don't know how to answer. Of course, there are excellent books out there. They were created breaking down, like you mentioned, this modeling technique, the query first approach, into like a lot more detailed steps that you can follow to drive how you define your schema. I think I kind of skipped some of that to package all of content into this presentation, but I think it should kind of fall in line with all the guides you can find in the official like books out there on Apache Cassandra, also on the documentation on the DataStax side, and so on. So yeah, I highly recommend to go there and find all of that query first approach thing described in detail. Yeah.
Mm-hmm. I think Dimitri just had a follow-up. He said, maybe we can add UUID 7 to supported types for Apache Cassandra. Yeah, definitely. It's a CEP. You can write it up.
Yeah, I mean, Apache Cassandra is pretty simple from the type. So what I used here is just a text type column, which is perfectly fine to do usual like UUID version 4 or UUID version 7. They are from the format exactly identical, just that the version 7 is kind of sortable
Yeah.
by time.
Yeah, it was a question for me. Yeah, I think it's perfectly fine to have a text version for this column. It just may be slightly more efficient if we can support it natively, because internally it means we can store it not as a text, but more
Yeah,
compact, long representation. Plus, we will skip a validation because when you are inserting text columns, Cassandra have to validate that it's a valid UTF-8 sequence, and we can just keep it and make it slightly even a bit more better. But it's perfectly fine. It's just a kind of idea for a possible improvement, and I think I will create a ticket for it.
Great. Thanks, Dmitry. Appreciate the question. I thought I saw somebody unmute. Was it Yifan? I just saw somebody briefly unmute. Yeah. So we're almost out of time. So I just want to take a moment to thank you, Hartmut, for presenting and bringing so much knowledge. It's probably like a 4-hour actual training that you kind of brought it into a 1-hour compacted partition. So thank you. And I want to thank all of the other co-organizers, Bernardo, Sohail, and Aaron, for collaborating on this project. We are always looking for speakers for upcoming sessions. We have a general idea for, every month we have kind of a theme. We have a developer theme, we have a contributor theme, we have a community theme. So if you want to do a talk that is focused around like for Cassandra developers versus the Cassandra, community versus the end user of Cassandra, feel free to, Apache Slack group is the best place to kind of talk about it. We are looking forward to the next meetup. I want to say that we have a general topic already chosen. We have a potential speaker, but there's March until December, guys. So plenty of time to get your talk in. And if you have an idea for a talk that may take a couple of sessions, let's talk about it. Let's see how we can break it up and, do it in, let's say, 2 sessions over a couple of weeks. So really glad to have this show back on the road. You guys have a wonderful week ahead, and we'll see you next month. The next meetup will be March 19th. Okay? See you guys soon. Bye-bye.
Thanks for having me. Bye-bye, everyone.